Okay. All right. So we are in section. Simplifying expressions, 11.2. Let's go back to see what the emphasis, by the way, on the final will be on this last part you haven't been tested on yet, which is algebra. Okay.
Can we go back to the assignment 11.1?
Sure. Which one?
Number 89.
89.
I got this.
Okay, this is the area where we were talking about the properties, commutative, associative, and distributive properties. And they're saying apply the appropriate property to simplify the expression. Here's the expression, 8 times 1/2 A. Okay, the way to do this is, first of all, ask yourself, what operation do I have there? Sometimes it's a mixture, but most of the time it's only one operation. The only thing that's going on here is multiplication, okay? Multiplication between the 8 and what's in parentheses, but even in the parentheses, you've still got multiplication. Okay. In that case, we should look at the properties for multiplication, and there's two major ones, and they are called commutative and associative. Commutative only applies to the order of things. When you're multiplying things, the left-right order simply doesn't matter. You can just switch them back and forth. However, associative applies to doing more than 2 multiplications, 3 multiplications, 4, 5, whatever. And that's exactly what's happening here. This 8 is getting multiplied by this, which is a product of 1/2 times A. So there's 3 multiplications going on there. All right. In that case, what you're allowed to do, basically, the associative property says you can multiply any 2 that you want to. It's a grouping property. How do you group it? It all comes from the fact that when you were kids, you were taught how to multiply by a table, but the table only had rows and columns. That means you can only multiply 2 things at once. That's it. And there are situations where you have to multiply more than 2, and that's the way it is. The way we get around that is say, okay, let's break it down to do 2 here and then multiply by another one and so forth. So the associative property says, instead of multiplying the 1/2 times the A, which you can't do if you don't know what A is, you can do this. You can multiply the 1/2 times the 8, and then take that and multiply it by the A. So in other words, 1/2 times 8, you can write it as 8 over 1 if you want to, and then cancel and so forth. That gives you a 1 there, it gives you a 4 there. So you've got 4 times A, and that is the associative property. Associating the multiplication with whatever 2 you've got, or you'd rather do. And this is the associative property of multiplication. Okay? So that's the answer for A. Any others?
Could we do number 79?
Number
79 on
79.
11.1.
Okay. Let me just hand out these sheets so that.
Good. Oh, 75.
75, okay. Be there in a minute.
No, that's not.
That was 75 for 11.1, right?
Yes, ma'am.
Thank you.
Do you want us to tell you when the book is wrong on its answers?
It doesn't really matter much to me, I can't change.
89 is wrong.
Actually, technically, I can. I can write them about minus. Okay. Now this is the distributed property. And the reason it's distributed is because we're multiplying a sum of things by some number. Distributive looks like this. You've got an outside number, call it A, multiplied by the sum of, let's say, three things, B, C, and D. Okay. That can be done by taking the A inside and multiplying each one of these separately. So this could be A times B, A times C, A times D, and then add them all together. In other words, the distributive property says it doesn't matter what you do first. You can add first, then multiply, or you can multiply first and then add. It's okay. Now, why is this that? Well, because this really means opposite. And opposite always means multiply by minus 1. So this is really a minus 1 multiplying that. Okay. They say, well, I don't have addition here. I've got subtraction. But remember, you can change subtraction to addition to the opposite. You could write this in the following way. Minus 5 plus, minus 5 cubed, plus a minus 2s plus a minus 3t. Okay, now you've got nothing but addition. So all of a sudden it fits that pattern over there. So we want to take the minus 1, bring it in, and multiply it by all those things. Now this is a fairly long, drawn-out process. You've got to do 3 multiplications, do 3 associative laws, then change the addition back to the subtraction. You know, there's a lot of little detail stuff if you want to do it step by step according to the rules. But this is the one where we say there's a quick trick here, and it saves so much time and cuts out so many possibilities of making a mistake that it's worth doing. And here it is. All you do is look at the sequence of signs you've got up there. And it doesn't matter whether it's subtraction or opposite, just look at the signs. You've got minus, minus, and minus. The effect of this multiplication with all those little detailed steps is simply going to be to change all those signs. That's all. That's all it does. So what's the result going to be? You can write it down. It's going to be 5 cubed plus 2s plus 3t. That's it. Change them all to plus. That's all it does. Now that occurs so often in algebra that it's worthwhile remembering the trick. It glosses over all the real stuff that's going on, all the distributive laws, all the associative laws, all that stuff. It skips over all that. But, you know, if you go through all that, you increase the chance of error. That's the problem. So to reduce the error, just look at the signs. That's all that happens. And that's one of the very few tricks that even your book tells you about, because they realize that it saves a lot of students' averages. Okay. Any others?
11.2, number 61.
61. Okay, we've got 4.4. Who teaches in here about consideration?
Geology.
I'm gonna need it.
Oh, there's
But
two
he
right
can
here.
teach it. That's what these erasers. Okay. Minus 0.9a plus 3.2. Okay, and I think I mentioned yesterday, when you're talking about algebra expressions, we took all letters and numbers. it's much more likely that the numbers are gonna be decimal numbers than they are whole numbers. Whole numbers is an idealization. It's what the book does to get you to stop worrying about the math so much and just understand the process you're going through. But in real life, that's the kind of thing you see. Because measurements taken today are all done with decimals. Okay, so what wants to happen here? The way the book describes it is combine like terms. Now, what are like terms? Like terms have the same letter, the same unknown or variable, whatever you want to call it, to the same power. Well, there's only one letter there, and that's the A. So there's nothing to combine it with. Therefore, it stands by itself. There's no like terms. But there are these two terms right here, 3.2 and 4.4. Now, those are just plain old decimals. Can you combine them? Well, I would hope so. That's why we did the section on adding decimals, right? So yes, they are like terms. These two are like. So how do you combine them? Well, you just do what it says to do. 4.4 plus 3.2. That's all. Just add them together. 7.6. You're still subtracting that 0.9a. There's no combining these two because this is a constant term. This one has what's called a variable in it, which means that letter can change depending on whatever else you're going to be doing with this thing. So we can't combine these. This remains 7.6 forever. This could change because that A could change. So that's why those two can't be combined. That's why we're done at that point. Okay, any others?
Can you change that, negative sign before the 0.9 to a positive?
You can, but then you'd have to change this to its opposite. You could write it like 7.6 plus a minus 0.98. Whenever you go back and forth between addition and subtraction, you change whatever it is you're adding or subtracting to its opposite.
Okay.
It goes both ways, though. You can go back and forth.
Why can't you divide 0.9 by 0.9 and 7.6 by 0.9, just whatever A is?
Why can't you, what was the next word?
Like, you know how usually you get the letter, no?
Just ask the
okay,
question, don't worry
so
about it.
0.9 divided by 0.9 leaves the A by itself.
Why would you divide by 0.9? This is a
Um,
very important thing.
yeah.
Why would you divide by 0.9?
Because I thought that's what you usually do.
Single out the A?
Single out the A.
Okay. 0.9 currently multiplies A, right? Right now, because we haven't done today's lesson yet, we have no reason to want to get A by itself. But today we'll find out there's a good reason to do it. Okay? So what you're headed toward is the next step, and the next step is solve the equations. And when you're doing that, yes, that's exactly the procedure you use. But here, we're just simply asked to simplify by combining like terms. And you have to do what the question asks. So the like terms of these two, combine 7.6, that's it, your job's done. If it said isolate the A or get the A with a coefficient of 1, then what you're talking about would be a good idea. Okay, so that's the next step we're going into. Anything else with these?
81.
81. All right. Now we've got a distributive law problem. 20A minus 4 times B plus 3A minus 5B. And the instructions are clear the parentheses and combine like terms. Now, they're actually being rather nice to you there because they're telling you the order to do it in. First, clear the parentheses, then combine like terms. The parentheses indicate that an operation has to be done. That's a distributive law. Distributive laws will always have parentheses in them, like that. So it means you got to do that multiplying process. And it hasn't been done here. You've got a B there, add it to 3A, but all of that has to get multiplied by the 4. So when they're talking about clearing parentheses, that's what they mean. Now, again, yesterday what I suggested is that you sort of ignore the subtraction sign there and just bring the 4 inside and do the multiplying, but keep the parentheses. that, I know it takes a little bit longer to do it that way, but it makes more sense in terms of not making a mistake. So I'm gonna bring the 4 inside. I'm not doing a thing with the 28. I'm gonna leave that the way it is, but I'll take that inside, multiply it by the b to get a 4b. Then I multiply it by 4 times 3a. Again, associative law kicks in. I can multiply the 4 by the 3 to get a 12a. And I have this thing trailing off on the end here. Okay, now the reason why I kept these parentheses is because I want them to remind me to subtract both of these terms. What you do to something in parentheses, you do to everything inside the parentheses. That's what parentheses are. They're grouping something together. So whatever you're doing, do it to the whole thing, every single part of it. So I've got to subtract the 4b. And I also have to subtract the 12a. And if I have a quarter for every time a student forgot to subtract the 12a, I would be sitting on a beach in the south of France. Okay? That's the big mistake. That's why I keep the parentheses. Oh, I've got to subtract both of them. I want my mind to think that way. I'm training the mind to say, that applies to both of these. Okay? I know I'm pushing it very hard, but I guarantee you this is where most of your errors are going to be on tests. Okay? All right, now we've dropped the parentheses because we've done everything we're supposed to do. We multiplied by 4 inside, and we subtracted both inside. There's nothing further to do. So you can drop the parentheses. You're done. Now, all right, now like terms. Here's a 20a and a 12a. Here's a 4b and a 5b. All right, let's get it all together now. So we've got an a box and a b box. We're going to put 20 of these a's in there, but we're going to put a negative 12 in there. Think of changing that to addition of the opposite. That would be a negative 12a. That's like FedEx coming by and dropping off 20 boxes of widgets, right? And then coming by a few minutes later saying, oh, I made a mistake and taking out 12 boxes of widgets, huh? So how many boxes do you have left? 8. 20 minus 12, 8 boxes of widgets. That's right. Likewise, minus 4b and minus 5b added together give you a minus 9b. So all you do is work with the coefficients. You work with the 20 and the 12, you work with the 4 and the 5, and get the right answers with the signs. And that's it. You can't combine a's and b's, right? They're not the same thing. Those are not like terms. So all of this stuff is that. That's the simplified version of that. Now just imagine that we're going into equations, which we are in a few minutes. All right, this is going to be on one side of an equation, and there'll be an equal sign. That's what makes it an equation, huh? And another one equally ugly over here. And you're going to be asked to solve the equation. Would you rather have this or this? Yeah, you get the point? That's why it's called simplification, right? So we have to learn to simplify this stuff up here to get to there so we can solve the equations, huh? Believe it or not, English word problems written in English can generate stuff like this. There is a way to construct an English sentence which requires a distributive law. And it happens. So therefore we have to be able to take care of that kind of situation. This is why people pay you money when you know math. You know stuff that they're not interested in knowing. All right, any others in 11.2? 13. All right. So it says, we've got 4p cubed minus 9p. The instructions are, list the terms, identify each term as variable term or constant term. Okay, well, we're going to list them. Well, here's one term. Terms are things that are added or subtracted, because subtraction is the same thing as addition of the opposite. So this is term 1. This is term 2. Okay, so the list would simply be 4p cubed, put a comma for the list, 9p. Okay? Or if you want, you can make it minus 9p, it doesn't matter. All right, now, we want to know, are they variable terms or constant terms? Well, they both have letters in them. This is a P, this is a P and a Q. So these are both variable. Because they've got something which could change in the course of solving a problem. So variable. Believe it or not, what we're doing is learning the language of algebra. And it takes a while to get the language down. It's important because whoever you have for your algebra course is going to be speaking algebra. And if you don't speak algebra, you'll miss, a third of the lecture because it's jargon. So you got to learn the language. Any others in 11.2? 73. Okay. We want to combine these things. And yes, there's A's and B's in two different places, so we should be able to combine them. But we have to be careful because they're involved in mathematical operations. We can't get to them right away. We have to do the operation first. In this case, just the draw. Okay? So let's start with the left-hand one here, just because in English we go left to right. All right. I've got a -2 out here. It wants to come in and multiply both of these things. That's why there's parentheses around it. I am, in this case, going to bring a -2 in. And let's see what happens. A -2 times A. Well, that's it. Then I'm going to add to that, because that's addition, a -2 times a 3B. And I'll write it like that. This I haven't done anything with yet. I'll get to it in just a minute. Just going left to right. All right, -2A is fine. Now, -2 times a 3B, I can associate multiplication with -2 and the 3. Using the rules of signs, that gives me a -6B. And I keep it in parentheses. I don't want two signs next to each other without something in between. Now, over here, this is telling me to subtract both of those. Okay. If I'm going to subtract 4A, I just simply write it as -4A. But this is addition of the opposite, where this would be the addition of a -5B. And I'm going to subtract a negative. What happens when you subtract a negative? You change it to addition of the opposite, which is adding a positive. So this minus and minus combined give me a +5B. Now, I could write out the steps to that. You can do it this way. I'm just a side thing here. -4A subtract 5B. All right, that's like taking a -1 and multiplying it by this and getting a -4A. Now, this one here, the way you could do that is change this to addition of a -5B and write this as a -1 times a -5B. So it's -4A, and over here, -1 times -5 is a +5B, which is what we have. Now, most of the time, people don't go through all this kind of thinking. They just simply say, oh, I'm subtracting a negative, minus a negative is addition of a positive. They just remember it like that, okay? But that's the detailed thinking that goes on behind it. All right, we're not done. Now we've got A's, those are like terms, and we've got B's, those are like terms. So let's get them together. So we have -2A's and -4A's, that means we're down 2, and then we're down 4 of the same thing, so we're down 6A's. -6B's and +5B's leaves us with a net of -1B. So all of this turns out to be that. And yes, the stuff that's difficult about this is the nitpicky stuff about signs. That's correct. No one likes it. I mean, this is not something you smile about, but it's necessary to get the equation solved. Any others? All right, so let's solve some equations here. Now what we're going to do is, they used to say on Monty Python, now for something completely different. We're going to approach this in a very unusual way. If you've seen Algebra 1 before, then you know what the little interesting approach is. And if you haven't, it may shock you. First of all, a definition of equations. It's a statement that two numbers or expressions, algebra expressions, are equal. Equal meaning the same. The simplest kind of equation you can have is something like x equals 7 times algebra. Okay? All that means is the left side is identically equal to the right side. So you could say that this is just an algebra way of writing this down. 7 equals 7. Well, no one's going to argue about that. I mean, that's obvious. If you can't agree on that, then you're from some other planet. And that's that. Okay. You can have far more complicated equations than that. And we'll be getting to, some that are pretty complex this week. You can do stuff like this. Suppose we have 2y plus 14 equals 20. Notice you can look at this one and see what makes it true. Well, of course, if I replace x with 7, I get 7 equals 7. It's obvious. Kids can see that, right? You can look at that one and probably not see what makes it true. Things are getting more complicated now. And if I threw in a few signs there, like a -2 and a minus for the 14 and all that, you certainly couldn't see what was true. Huh? That's just a bit much than our minds want to do. That's enough. So what we need is a method of taking an equation which is like this. And this, by the way, is a simplified equation. There's nothing to do there. It's as simple as it gets on the left, and obviously as simple as it gets on the right. So there's nothing complex here. But still, it's hard for us to see what the answer is. So our concept is this. This kind of equation, which has the unknown on one side with a coefficient of 1. See the coefficient of 1 there? No, of course you don't. It's very small.
That's right.
There it is. There's a coefficient of 1 there. Right? It's the one that we never write. All right. That's called isolated. So the entire equation is known as an isolated equation. Because the unknown is multiplied by 1, and there's nothing added or subtracted or anything else. It's just multiplied by 1. That's it. This equation is not an isolated equation. Here your unknown is y. It's multiplied by 2. And then you've got the addition of 14, and so forth. So there's a lot of things sort of clogging up our vision of what the value of y is that will make that true. All right. This is an equation that needs to be changed into an equation like this. This particular kind of equation is called a compound equation, but that doesn't make any difference. The important thing is we want to change it. This is the kind of equation that comes from a real-world situation. And fine, all right, so English gives us that kind of an equation. That's not what we're going to solve. That's not easy enough for us to see the answer. So we have to do something to change it. All right, more definitions. Let's keep going here. An equation solution is the number which makes the equation true. And there could be more than one number. For example, this one obviously is true when you replace x with 7. This one, not obviously, is true when you replace x with, can anyone see it? 3. That's right. So if I said, well, let's try a 3, or y equal to 3, and put it in there, I get 2 times 3 plus 14 equals 20. This works. 6 plus 14 is 20, that's right. So that makes it true, yes, this is a solution. And that's all a solution has to do. It has to go back to the original equation. When you put in that number for the unknown, it's true. That's it, that's the solution. Our scheme, you might call this the equation solving strategy. The way we're going to look at this is to go from a complicated equation to an isolated equation. By using four, I'm going to call them legal operations. Legal operations guarantee that you cannot possibly change the solution by using them. Okay? So if you start out with something like this, 2y plus 14 equals 20, we're going to massage this thing mathematically and get it into a form where we have that, y equals 3. A simple equation, an isolated equation. And we're going to do it by certain steps, and we'll learn the steps. But these steps guarantee that the solution of the original equation is not changed by doing this. Okay, that's why I call them legal operations. Okay, they come with a guarantee. All right, let's take a look. Your book does another definition here. Okay, let's do it. Linear equation is one where the variable is to the first power. And this is an example of it. Here you've got the variable, it's called y. It's to the first power. There's no y squared there, just first power. And all we're going to be doing in our class is linear equations. When you get to Algebra 1, first few weeks you'll deal with linear equations, and then you'll start building up to be able to solve what's called quadratic, which were the variables to the second power. And that's all you do in Algebra 1. You get to the quadratic. Third power, fourth power, and so forth. Extremely difficult. Second power is doable. The rest of them are much more complicated. Okay, here's the idea. If we went over to the physics building, up to the second floor, there's what's called the chemistry division. And years ago, they used things like this. This is known as an analytic balance. And it's a kind of scale. So you measure things, you measure weights and so forth. And what you do is you come in with, we're being in California, we go up to the Sierras and get some gold dust out of the river, right? There's still some left, right?
Yeah.
Fool's gold.
Fool's gold, right? All right, so you sprinkle the gold dust on there. Of course, it goes like that, huh? Because this weighs something, there's nothing over there. So let's suppose we're in the assayer's office, and the assayer has a bunch of Bureau of Weights and Measures standard weights. They're little gram weights and 5 grams and 10 grams and stuff like that. And they look like little cylinders made out of brass. And they have a little handle on them so you can pick them up and so forth. So the assayer puts some weights over there and everything comes back into balance. And the needle up here is pointing straight up. And at that point, he says, oh, well, you've got 2 grams of gold dust. and I will give you so much money for them. Of course, they get a lot of money for gold. So that's a way of balancing things with standard measures and getting the amount of gold dust that's over here, which we can't actually determine. Okay. If I use this model, believe it or not, is a physical model in the physical world, which is very similar to equations. Okay? When you're talking about equations, you're talking about things being equal. Left side equals right side. That's like the two scales. Okay? You can tell right away that if I change anything in this picture, I'm going to have to change both sides. If I pour a little bit more gold dust on it, I'm going to have to put another weight over here in order to get things to come back into balance. Huh? Right? Algebra means, what's the definition of it? Bringing back into balance. That's where they get it from. So the technique we're learning today is the very essence of algebra. All right, what can I do? Well, let's say I put 2 grams more gold dust on. I sprinkle it on. And I take a 2-gram weight and I put it over here. Okay, it goes out of balance temporarily, but as soon as I put the 2-gram weight on, it comes back into balance. Huh? What have I done? Added the same amount to both sides. Okay. If I subtract, let's say, exactly 1 gram from this side and take a 1-gram weight off this side, still okay, it'll come back into balance. Huh? In other words, there are certain operations you can do to the left and right side and guarantee balance. Okay? Guaranteed left side and right side are still equal. However, with these operations, what's on the left side is going to be different from what it was to begin with, and so is what's on the right side. Right? So you're changing what happens on each side, but keeping the balance of the two sides. And that's the key to this whole thing of algebra. So let's say I start off with something like this. Suppose I have x minus 7 is equal to 10. All right, that's not isolated, because you get subtracting 7 from the x. I want to get to an isolated situation. I want to start doing a series of steps so I can finally get x is equal to some number. So just call it the number, and that'll be the solution. All right, what I've got to do is undo this subtraction of 7. So the way to undo a subtraction of 7 would be to add 7. Yeah. So I'm going to add 7 to it. I'll move this over a little bit. I'll add 7 there. But because of the balance scale thing, I have to add 7 over here. Or else it'll certainly go out of balance if I don't do that. So this adds to nothing. Ah, there's my x. 7. There's my answer. Isolated. You say, well, that's too simple. Yeah, it's a lot simpler than the simplification stuff that we were doing, right? Yeah. Yeah, that's it. That's how it works. It's that simple. Let's try a few more. And you'll see that this is amazingly easy. All right, we'll start out with z plus 11 is equal to 14. Let's figure out what value of z makes that true. The key is, don't try to figure it out in that equation. Change the equation to the isolated equation, and then you'll have the answer. So in order to get rid of this problem of the addition of 11, I'm going to subtract 11, because that undoes addition. I'll do it vertically this time, just to save a little space, that's all. Okay, so I've got plus 11 minus 11 adds to nothing, so I'm left with the z, that's what I want. And 14 take away 11 is 3. 3 is the answer. Now I've got my isolated. It's that simple. Now, of course, you can throw in a few signs here and there, but that doesn't really complicate it too much. Let's say a minus 8 equals q plus q. And we want to know what q makes it true. You can sit there and strain your brain trying to figure it out. Actually, strangely enough, the thing that works is to say it in English. I know, you've never heard me talk about English like that, but English works there. What number do I have to add to 2 to give me minus 8? Well, let's actually do it mathematically instead of spraining all the little gray cells. All right, I've got the key there and I've got the additional 2. What I want to do is subtract 2, right? So here we go, subtract the 2, but I have to subtract the 2 there. Okay, 2 minus 2 is nothing, and then you've got nothing but q there. Now, this is a minus 8, subtract a positive 2. Careful. That's a minus 8 plus a negative 2, right? Change to addition of the opposite, and that is negative 10. So when you throw in a few signs, you have to be careful with the signs, you know, but we're still doing the same thing to both sides. All right. Of course, the idea is to get used to this. Let's do one more, then we'll have some homework. Let's throw in a fraction. We haven't seen a fraction in a while. Now that's enough to stop probably everybody in the class, right? Put a few different denominators there, and there's nothing but silence, right? Okay, but keep the process going. The process is more important than a particular answer. It's the process we're after here. The process is to isolate that m. To do that, I would have to subtract 3/10. 3/10 minus 3/10, that's 0. I've got my isolated m. But I must do it over here too. Agreed? Okay, this goes to nothing. There's the m. That's what I want. Now I've got minus 2/3, subtract 3/10. Well, we've got to get an LCD. That's the only way you can work with those. That's why we had to study LCDs. Huh? So the LCD for 3 and 10 is? That's right. So let's convert to the LCD here. Have to multiply by 10 there, and of course there, and by 3 here, and 3 there. So I get a minus 20/30, subtract 9/30. And the way we do that is put everything over 30, minus 20, subtract 9. Okay, sorry, I don't do subtraction, I do addition of an opposite. Minus 20 plus a minus 9/30. And that becomes a minus 29/30. That's why we couldn't see the answer, because there's just too many steps involved, too much going on. But that's the answer. If you put minus 29/30 back in there for m, believe it or not, that would make that equation true. It takes more time than it took to solve the problem, but that would make it true. All right, let's do some homework. This is 11.3.